Okay, so let's go ahead and get started. Again, I'm just going to record today's session. Let's maybe start with homework. Does anybody have questions on the written?
82.
Which number, Chris? 82? Okay, Janae, you asked about that same problem? Okay. Any other questions on the homework problems? And then once we get through that, we'll dig through some review. Okay? 55? Okay. So, I must open the textbook. I'll do these in order, so I'll talk about 55 first.
Wait, is this due today or tomorrow?
Tomorrow.
Okay.
Yeah. Yeah, so at least you'll have the rest of the day to get it done and hopefully finish it and have some time left over to study too. Okay, so 55. So this is the 4.5 homework, number 55, and let me see if I can, unless someone has it, it's solve 1/3 tangent
4t
4t
plus pi over 8
plus pi over 8
equals 2.
equals 2, and it's on the interval from
0 to pi over 2.
Okay, so you're looking for solutions on the interval from 0 to pi over 2. Okay. Why 0 to pi over 2? Well, I guess, first of all, we could think about how many solutions you're going to get. Since your value of capital A is 4, the period of the function on the left, this transform tangent, would be pi over 4. Okay. There's actually going to be 2 solutions on the interval from 0 to pi over 4, so I think this equation will actually have 4 solutions from 0 to pi over 2. Okay. So we'll find the first 2, and then we'll use the period of this maybe to get a couple more. Okay. Or we'll just use the period of tangent to get a couple. So let me see if I can do this here. So first of all, you need to isolate this tangent 4t plus pi 8. So I can multiply by 3 on both sides, and I'll get tangent 4t plus pi 8 is equal to 6. Okay, so isolate the tangent portion. And we can first find 2 solutions. Okay, using our first solution, we'll be given, well, the road to the first solution. So we can first solve for this 4t plus pi over 8. Okay, so we'll be able to find 2 solutions. 4t plus pi over 8, we'll be able to find 2 angles. Okay, that equals. So the first one will always be 4t plus pi over 8, right? I'm treating that as some angle theta. And one solution is going to be arctan of 6. Okay. And then the other one is going to be 4t plus pi over 8. And then once you know one angle, how do you find another one?
You take the pi plus 2.
Yep, so you'll take this first solution, or the first angle, arctan of 6, and you'll do pi plus. Awesome. Right, we're treating the 4t plus pi over 8 as an angle. So there's 2 solutions to 4t plus pi over 8, or tangent 4t plus pi over 8 equals 6. First of all, arctan 6 and pi plus arctan of 6. Okay, so first of all, I'm going to solve for t in both of these expressions before I even plug this in my calculator. Okay. I guess you could technically plug it into the calculator now. Now, do they say to... They don't really tell you how to round, do they?
No.
Okay, so, I'm okay with maybe just round to 2 decimal places. Okay. So the first one, I'm going to subtract pi over 8 and divide by 4. So t is going to be arctan of 6 minus pi over 8, and we can divide that whole thing by 4.
0.25.
Into 2 decimal places, you get 0.25. Okay. And then the second one, I will subtract pi over 8. I'll just subtract it from pi, and then I'll again divide by 4. T will be, well, pi minus pi over 8. Pi is 8 pi over 8 minus 1 pi over 8. When you subtract pi on the right, you'll get 7 pi over, when you subtract pi over 8, you'll get 7 pi over 8 You still have the plus arctan of 6. And then that whole thing divided by 4.
I got 1.04.
Okay.
Which
You
is
get
in the
1.04?
range. Which is
Okay.
in the range.
Yeah, those are both certainly in the interval from 0 to pi over 2. Now, how do I know there's 2 more solutions? Well, there's always 2 solutions over a function's period. Okay, but since you have a equals 4, the period of this transform tangent is pi fourths. So you get 2 solutions from 0 to pi fourths. You'll get another 2 solutions from pi fourths to pi over 2. So what I'm going to do is I'm just going to take both of these, and I'm just going to start adding with the period pi over 4 to get the other 2 solutions. So the other 2, so these are the first 2. And then the other 2 solutions, I'll take t equals, well, let's just start with 0.25 and add pi over 4. And actually you get this one when you do that. Okay. So actually, rather than do that, let's actually, again, this one just gives me the 1.04, so I just got nothing. Okay. So I'll start with the second one. So I'll take 1.04 and I'll add pi fourths to that to get another solution.
That's out of the range. Yeah.
1.82?
The range is 1.57.
Oh.
Yeah.
2 solutions.
Oh, hold on. I'm actually mistaken here. Because remember, tangent theta has period pi. But on the interval from 0 to 2 pi, let's see, tangent has asymptotes at pi over 2 and 3 pi over 2. And it does something like this. So through tangent's period, there's really only one solution to a given equation. Okay, so you actually have to go through twice 2 periods of tangent to get 2 solutions. The period of this is pi over 4. This is an interval of length that's double the period. So really we should just have 2 solutions. So I actually misinterpreted that one. Okay, and you'd see if I took these and I kept adding the period pi over 4, like Kirsten said, we're going to be outside of this interval. I don't think it's a bad thing to have you guys see me try something and fail every once in a while. Be wrong, I got to be wrong too sometimes. Okay. So does that make sense to everybody? This is actually running through twice the period of this function. That's why we'll get 2 solutions. Just like for tangent, the period's pi, but you get 2 solutions through 2 periods. Yeah, Maddie?
So, looking at just from 0 to pi over 2, where it's just the exponential growth, that first time of tangent.
From 0 to pi over 2?
Yeah. Why are there 2 solutions there?
No, there's 2 solutions through...
Because it says from 0 to pi over 2 in the original statement.
But that's through 2 periods of tangent 4t plus pi eighths. The period of this is pi over 4.
Okay.
So 0 to pi over 2 is running through 2 periods. Right? And just if we come back to the original tangent, its period is pi. So you get 2 solutions through twice the period, right? If I took my positive 6 and I look at this horizontal line, you intersect the graph twice on the interval from 0 to 2 pi. So tangent only has 1 solution through its period, and then if I double the period, we'll pick up a second solution.
Really quick, Chris. Why is it pi over 4 exactly?
Okay, so if we look at a transformation of tangent,
Oh, right, I forgot it's tangent, never mind.
tangent A theta minus
Yeah.
B, you always take the period of tangent and divide by absolute A.
Yeah.
So this one has period pi over absolute A, pi fourths. So 0 to pi over 2 is twice the period. You should get 2 solutions. If I went from 0 to pi, I'd actually have 4 solutions. Okay. So actually you can stop there. And then 82? Yeah. Okay. Okay, so 82. So this is that amount of daylight as a function of the number of months, or no, as a function of the number of days since January 1st. And this makes sense, okay, why this is going to be a periodic function, because what happens with daylight, right? Right now, I think we're actually getting more and more daylight every day. Eventually, that's going to hit a maximum, and then the amount of daylight is going to start decreasing to a minimum again, and then it repeats. It'll increase and decrease. So if you think about the amount of available daylight as a function of months, you should see a sine curve, because it keeps fluctuating up and down. Okay, and then what was the function? Does anyone have it in front of them? What is it? Sorry.
d of t equals 2.8 sine 2 pi over 3 minus 65 t minus 81 plus 12.
T minus 81 plus 12. Okay, so here's a model. This is d of t is the amount it's the available daylight since t equals 0, which corresponds to January 1st. So this is the available daylight, so the number of daylight hours since t equals 0, which is corresponding to January 1st. So t equals 365 would bring you back to January 1st. Now part A just says how much, was part A a problem really? How much daylight is present when t equals 31, so 31 days after January 1st. Well, if they're giving me the t value and I need how much daylight is present, you just plug 31 into this function and evaluate it. So the answer is d of 31, 2.8 sine 2 pi over 365, 31 minus 81 plus 12. And then you'll have to plug that into your calculator. Make sure you're in radian mode.
I got 9.233.
You get 9.233.
I don't know if anyone else got something different, but that's what I got.
How much, like, how close do we have to be?
Just round it to a couple decimal places.
I like 3 decimals, that's why I chose 3 decimals.
I'm not really picky. I mean, if I don't really say, I would at least do 2 decimal places if I don't say.
But there can be negative hours.
So I'll double check it just to make sure.
Yeah, actually I think I got negative 9 now I think about it. And
I got
negative
2.77.
Yeah, I got.
Okay, I'm going to double check it. So I plug in 31. 31 minus 81 is negative 50, right?
Mm-hmm.
I get 9.876.
This size close.
Okay, so double check that again, Kirsten, but I
Yeah,
think we're
do it
going to
again.
get,
Yeah, that's what I got.
Parentheses.
I got 9.88.
so there's actually 9.88 hours of daylight 31 days after January 1st, according to this model.
No, I still got the same thing.
Yeah,
Oh, I know what it is.
Are you in degree mode or?
I'm in radian. I put 28 instead of 2.8.
Oh, okay. That'll
Maybe that'll
change
change
things.
it. Okay, thank you.
Yep. So part A is just plug 31 into the function. I think part B is the more challenging
On
one.
which days will there be approximately 14 hours daylight?
Okay, on which days, or basically how many days after January 1st, and it says approximately, how many hours?
14.
Okay. So instead of telling you what's the output for a particular input, this question is that typical question, when the output of the function is 14, what would be the input value of t? Okay, so you're going to take your function 2.8 sine 2 pi over 365 t minus 81 plus 12 and set it equal to 14. Now, intuitively, how many solutions should there be? 2, right? Think about a whole year. The daylight increases to a max, so at some point the amount of daylight will achieve and surpass 14, and then the amount of daylight will decrease again, and you'll achieve 14 hours of daylight one more time before the cycle begins again. Okay? So there should be 2 solutions. So what do I want to first isolate?
The sign.
Okay, first we'll isolate the sine piece. So first that whole sine 2 pi over 365 t minus 81. You'll subtract 12 and then divide by 2.8. I'm just going to leave it as 2 over 2.8 for now. So I'm going to wait till the very end to do my approximations. Okay. And then where do I want to go from here? So we're going to treat this whole input right here is just representing some angle being plugged into sine. We'll have to solve for that angle first and then solve for t. Okay. So the first angle theta, which is the 2 pi over 365 t minus 81, should equal what? So it'll involve the 2 over 2.8, but we need to plug it into arc sine. Okay. This is just the whole idea of when you go from a function to its inverse, the input becomes the output, and the output becomes the input. So we're swapping inputs and outputs. Okay, and then there will be a second equation you'll have to solve. You can take your angle. And Kirsten, you said you're going to take that same thing that I'm treating as an angle theta. Instead of arc sine, we're going to do pi minus the arc sine of 2 over 2.8. And then I have to solve for t in both of these. And I should, once we solve for t, we'll get the number of days since January 1st, where there is approximately 14 hours of daylight available.
Do you want the actual date, like August 7th or something?
No.
Or you fine with the approximation?
Just give me the number of days since January 31st, that's fine. I don't really want you to go, some months have 30 days, some months have 31, and I don't really think it's worth our time to literally count through that. So yeah, just the values of t will be sufficient to me. Down here, you can first multiply both sides by the reciprocal of 2 pi over 365. If you want to get rid of something that's a multiple on one side of an equation, multiply both sides by the reciprocal. So t minus 81 is going to be 365 over 2 pi arc sine 2 over 2.8. And then the last thing you do is just add 81. And there would give you the first solution, the number of days since January 1st, or how many days after January 1st are there, would give you 14 hours of daylight, so that'll be the first number of days.
Chris?
Yeah?
It just looks like 265 instead of 365.
Oh, oops. My bad. It should have been a 365 over 2 pi, thank you.
Just in case.
Mm-hmm. And then I'll do the same thing over here. T minus 81 is going to be 365 over 2 pi times this pi minus arc sine 2 over 2.8. And then I'll just add 81 to both sides. And then you have to plug this stuff into your calculator. And like I said, technically these are just linear equations. I'm not going to spend a lot of time in class going through all my little steps that we did. So again, I'll just one more time. I multiplied by the reciprocal and added 81 in both of these equations. And then I'll leave it up to you to put it in the calculator. Chris, or has anybody done the first one?
Yeah, I got about 119. I got 127. We're getting different.
Yeah, I got weak.
Yeah.
Is your calculator in radians?
Yeah.
So you have to be careful about how you're entering it.
Yeah. I got
Now, hold on, let me ask this first. Does anybody really want me to spend the time putting something in my calculator right now, or should we move on and go over strategies for how to solve things? I mean, this is, at this point, it's just plug stuff in your calculator, and I don't know if it's really time best spent in class. Yeah, move on. I agree. Okay. So, review questions. Anybody need a copy of the review that I passed out yesterday? I just printed the review from the textbook out.
Oh my god, that's too much. Okay.
Oh, sorry, did you get this, Jesse?
Yeah, I got it.
Okay. And Jesse, I have some stuff for you, some homework before you leave. Make sure you grab it. Okay. So, what sort of things should we talk about? So, even just looking through this summary, let's just go through that real quick. So, first section was learning about angles. Okay, and then it gives you how you originally defined the radian measure of an angle as the arc length over the radius. And then you can also find the formula for the arc length as the radius times the angle. So anybody want me to go over that fraction of a rotation stuff or how to find arc lengths? I think the hardest thing in that first section is if you have some circular, like a wheel rotating, and you know the number of revolutions over a period of time, you should be able to find the speed of the distance you'd be traveling on the edge of the circle. Does anyone want to see one of those quick?
Oh, sure.
Okay, so hold on. What was your question, Maddie?
Are we going to be given like formulas, or will we have to memorize them?
We'll have to know the formulas.
Okay.
If you're moving on, it's probably in your best interest to really have this stuff nailed down because if you go to Calc 1, you need to know everything from Pre-Cal 1 and Pre-Cal 2. If you go to Calc 2, you need to know everything from Pre-Cal 1, Pre-Cal 2, and Calc 1. If you go to Calc 3, you need to know everything from Pre-Cal 1, Pre-Cal 2, Calc 1, Calc 2. So yes, typically I like to make students kind of try and know as much of this as they can rather than depend on no cards. Okay, so let's do one of these problems. I guess I can say a wheel with radius 2 feet rotates through 1 revolution every, I don't know, we'll say 1.2 seconds. Okay, so that's the first assumption. So I tell you a wheel with radius 2 feet rotates through 1 revolution or 1 rotation every 1.2 seconds. Find the rim speed of the wheel. So if the wheel was rolling on the ground, basically this is just saying what speed would you be traveling, or what speed would the wheel be traveling. So find the rim speed of the wheel in, let's say, feet per second first. I could also have you convert that to miles per hour, but typically on the test, I don't really want you having to do all those unit conversions. Okay, that's something you should know coming in, so I don't want to focus on the unit conversions. Okay, what do they call that again? Dimensional analysis or something like that? Okay, so we'll just use the given units, feet and seconds. And I want to find the rim speed of the wheel. And again, the idea is, right, take some point on the wheel, how fast is that point going to be traveling around the circle? That's essentially your rim speed. Okay, so first thing you need to do, did I break this up in kind of a 3-step process? Okay, find the number of revolutions per second. Okay, so there is 1 revolution every 1.2 seconds, which is 1 over 1.2 revolutions per second. Right, so how many times are you going around every second? That's step 1. So you take the number of revolutions over the units of, or the amount of time, and that gives you revolutions per second. And then what did I usually do in step 2? If you know the number of revolutions per second, this is essentially your fraction of a rotation. Now you should find the amount of radians that you rotate by every second. So find So I hear some folks talking, what formula is going to be really useful here? So you can always find the angle in radians if you take the fraction of a rotation p and multiply it by 2 pi. Okay, so the angle theta in radians that you rotate by per second is going to be this 1 over 1.2 times 2 pi, and that's how many radians that we're going to rotate by every second. Essentially, I'm multiplying this ratio, or this, I'm multiplying 1 over 1.2 revolutions per second times 2 pi radians per revolution. That's why the units of revolution are going away if you're thinking of your dimensional analysis. And then finally, step 3 is find the, I guess, arc length traveled per second, which gives the speed. And which formula is useful there? So you've got a formula involving an angle and the fraction of a rotation. To find the arc length traveled per second, you're going to want to use the formula S equals r theta. That's going to tell you how much distance you traveled around the circle for a given angle. So our speed at the end here is just going to be take your 1 over 1.2 times 2 pi radians per second, and then you're going to multiply, that's your theta, and then you're going to multiply it by the radius of 2 feet. And that'll give you your speed, or the arc length you travel per second. So times the radius, let's just do it this way. So I'll multiply that by 2 feet, and I'll get 4 pi over 1.2 feet per second. And then I don't know if anybody's got an approximation to that.
I got 10.47.
You get 10.47?
At least I do.
Okay. I mean, I can double check it too.
I'll double check it. Yeah, not that bad.
Okay. So it's kind of the 3-step process. You're finding your fraction of rotation per second. Find the angle you rotate by per second. Find the distance you travel per second. So the first step is just taking number of revolutions over the amount of time to complete those revolutions. The next one is just multiply that value by 2 pi to get the angle rotated, and then multiply by the radius to get the speed. Somewhat familiar? I know it's been a while since we've done it. How about conversions from radians to degrees to radians? Is that worth our time? Okay, right, it's multiply by 2 pi over 360 or 360 over 2 pi, depending on which units you need to cancel. So what else did we do? So we learned how to basically label our unit circle with all the special angles and the special points. I think for the most part everybody did that pretty well on the quiz. So are we okay there? How about real quick, because my guess is the graphing stuff is probably number one. As I've noticed, that is probably the thing that people are struggling with most. Now, I don't know how people are doing on section 4.5 because I haven't seen your work yet. Okay, so once we do a couple examples of graphing stuff, maybe we'll take a couple questions on section 4.5. So,
Do you go over like functions with
With the reciprocal trig
Yeah.
functions
And then the even odd identities, that came up at the end of 4.5.
Yeah, so for instance, like even odd identities, well, they're on the paper. Sine's an odd function, the minus can come out. Cosine's even, the minus can be thrown away. And tangent is also odd. So what's a trick you could do if you wanted to say do cosine of minus pi thirds? If I want to use even odd identities. Just throw away the negative. This is the same as cosine pi over 3. That's a special angle. You should know that using the unit circle, cosine pi over 3 is 1/2. Okay. The way that I remember those pi thirds and pi sixths is I know that sine of pi over 6 is 1/2 and cosine pi over 6 has the root 3 over 2, and then it just flips around for pi over 3. So I remember one of them. I remember the values of sine and cosine for pi over 6, and then I switched them to get cosine and sine of pi over 3. Cosine and sine of pi over 4 are both the same, right? They're both 1 over root 2. And then you can use reflection properties to get all the other points on the unit circle for all the other special angles. What if I did something like sine of minus 4 pi thirds? Now you could think of a negative, a clockwise rotation of 4 pi thirds. Ben?
Are we gonna have to fill out a unit circle on the exam
No.
tomorrow?
You will be expected to know it, but I will not have a question where you fill it out.
All right.
You'll have questions like this where you have to maybe use some properties and know your special values on the unit circle. So what do I do with this one? So pull the minus sign out. And then you'd have to look on your unit circle. So let's see, 4 pi thirds is going to be, I believe, in the third quadrant. And that's related to the angle pi thirds. And the coordinates of the point up here are cosine pi thirds is 1/2, sine is root 3 over 2. So if I reflect over the y-axis and over the x-axis, these coordinates are just going to both become negative when you come down here. So sine of negative 4 pi over 3, using the odd properties, minus sine 4 pi over 3, which is negative minus root 3 over 2. So you end up just getting positive root 3 over 2. How are we on time? What do we have left?
5 after.
So you got 15. Let's get to the graphing stuff. It's not a lot of time to get through this. Also, before we run out of time, office hours today is going to be 1:30 to 2. I have to leave for a meeting, and then it's going to be from approximately 3:15 to when the TLC closes, I believe, at 6 p.m. Okay. It might be closer to 3:30, but I'll try and get out of my meeting as quick as I can. Okay. So I'll be in the TLC those hours today. Okay, we got to get to the graphing. Okay, and again, there's a lot of stuff we didn't have time to go over, but all right, so what if I want to, let me just pick a graphing problem on here. Is there one where they say sketch the graph of something? Yes, 22 to 27. So let me take one that has a, so here's what I'm going to do. We're going to do two at once because 23 we can actually get two problems out of the way. So what if I first said, so this is a variation. We'll do the problem plus an extra one. So what if I said graph 2 minus secant of pi fifths theta plus 2 pi fifths? And you'll see why extended it or varied the problem to this, because if I want to graph this function, what do I have to graph first anyways? Yeah, remember step 1 is to first graph the graph of cosine with the same transformations applied. So we'll graph, and can I reorder this? It's going to be minus cosine, so I'm going to do the plus 2 on the end. And then I can factor pi fifths out of the inside parentheses and get theta, I think, plus 2 left over. Have a plus 2 on the back. So I did two things. We're switching secant to cosine. I'd put the plus 2 at the end, and I factored out the pi fifths from the inner parentheses. Okay. And then hopefully this will tackle kind of both, like how do you graph a transformation of cosine, how do you graph a transformation of a reciprocal trig function, and we have a reflection in there. Okay. So a couple things we're going to need. You need to know your fundamental cycles of sine, cosine, and tangent. You need to know that cosine starts at a max, a quarter way through the period you're at the middle, halfway through a period you're at the min, 3/4 of a way through the period you're at the minimum, all the way through a period you're back at a max. So that's my fundamental cycle of cosine theta. And again, I just use that basic idea of find your phase shift, always take your period, break it up into a fourths, and then you add increments of a quarter period to your phase shift until you've gone through a full cycle or full period. So now we got to find the phase shift of this. The phase shift is 2 units, and because of the plus 2, we're really going left. So our first cycle on the graph is going to start at -2. And then we're going to trace one cycle through the period of this. Step 2 is we're going to find the period. The period of cosine is 2 pi, and you always divide by absolute A, which is 2 pi over pi fifths. Dividing by a fraction, you instead multiply by a reciprocal. The pi's cancel. You're just left with 2 times 5, which is 10. And there's no horizontal reflection, correct? But if there was, would my fundamental cycle change? Cosine's an even function. Horizontal reflections do not change the shape of the fundamental cycle. So even if there was a negative in here, it wouldn't do anything, but the vertical reflection will. Step 3, we need the amplitude. So the amplitude, and I've seen this on the homework, a lot of people are not doing absolute value of C. Amplitude is always a positive number. It should never have a negative. And that's the absolute value of -1. So the amplitude is going to stay 1, just like it was for the original. I would maybe make sure you note that there's a vertical reflection here, since C was really a negative number. Okay? And a lot of people miss that. Not a lot of people, some people miss that on the homework. I don't want to say a lot. Now, throwing in that vertical reflection is going to change your fundamental cycle to that instead. So you're going to start at a minimum at your through a fundamental cycle or through a cycle. Okay? And then what's the last thing I need to note? So I've taken care of A, B, C, the vertical shift of 2. And rather than talking about vertical shifts, I just talk about the midline, which is going to be 2. We shifted the graph up 2 units. Okay. Now when you graph these, what I want you to do is I want you to first throw down your phase shift. Oh, did I do the wrong direction?
Yeah.
Yeah. Really, we're supposed to start over here at -2. And what's our period? 10. I'm going to have to break that up into fourths.
You're doing
which would be 2.5. So I'm going to go 2 units to the right plus a quarter unit. Here's 0.5. I add another 2.5 units, which is about the width of my marker. I'm going to be at 3. I add another 2.5 units. I'm going to be at 5.5. And I add one more quarter period. We'll finish a cycle at 8. Thank you. So label your phase shift and keep adding a quarter period till you've done it 4 times to go through a full period. And then now what you're going to do is one cycle of our graph will be completed from -2 to 8. Now, let's see, what was our midline? I have to go up 1, 2. Our midline was +2. You can sketch that in.
Start at the bottom.
And then at our phase shift of -2, we're going to start, since we had a vertical reflection at a minimum value. Starting from the midline, I go down 1 unit at -2. That's where the graph starts. Quarter way through the period at 0.5, you're at your middle value. Another quarter way through the period, you're at your max. Another quarter of the way through, you're at your midline. And then finally, when you've gone through the full cycle, you'll be back to +1. There's one cycle of the transform cosine graph. And is it really that much more work to sketch the graph now of the transform secant? So I think what made section 4.4 difficult was if you didn't really nail transformations of sine, cosine, tangent down, that made it difficult to do the transformations of secant, cosecant, cotangent. Now where are all your asymptotes going to be?
Where it intersects with the midline.
Where you cross the midline, because if I was going to graph secant from cosine, secant's 1 over cosine. Wherever you're on the midline, you're going to have a vertical asymptote. So you'll have vertical asymptote at 5.5 and 1 at 0.5. And then this piece of the graph that's decreasing becomes an increasing piece. And it approaches the asymptote as you approach 5.5. From this maximum, you're going to curl up and approach the asymptotes. And from this minimum, I'll again approach my asymptote of 0.5. There would be one cycle of the original graph. Okay. We still have 5 minutes. Oops, sorry, Chris. Anything else? If you look through the review real quick. I could do the same thing too. Make sure you can go backwards. If I'm given a transformation of sine or cosine, make sure you can go backwards and recover the algebraic form. How about a Ferris wheel problem?
Are we gonna have application problems?
Yep. I can guarantee you there'll be like either there'll be like a Ferris wheel problem and there'll be like a rim speed problem like we did at the beginning. Yep. Now, I don't know if we can do this in 5 minutes, but we'll get as much as we can done. Actually, there's probably a Ferris wheel question on this review. See if I can find one.